For our next session, we will have the inaugural lecture of Raymond Song Chair Professorship of Distinguished Research. We'll first invite President Chen back to the stage to briefly talk about this exciting new program.
Alain Aspect and Alain Aspect, and also the Vice President of University of Paris, Sacré, Professor Banassar, and Director Paris of French Office in Taipei, and the faculty and the staff. Good morning.
Good morning.
Well, I took the wrong one, so so I still need to read the notes. Yeah, National Taiwan University marks the very exciting first chapter of the Raymond Song Chair Professorship of Distinguished Research. We are honored to have Nobel laureate Aspect as our historical first recipient, actually the first one. Okay, and who will deliver his inaugural lecture entitled "From Einstein and Bell to Quantum Technology, Entanglement in Action." It looks like a movie. Yeah. As I just introduced Professor Aspect on his innovative experiments with entangled photons, which confirm Bell's inequality violations and provide the crucial evidence for the non-local behavior of quantum particles. The groundbreaking discovery makes Professor Aspect to be honored with the 2022 Nobel Prize in Physics. The Song Chair Professorship Program was made possible through the generous support from the President Raymond Song, the founder of Lighter Technology. President Song understands the quality of higher education could affect the future development of Taiwan as well as the world. Also, he recognized the profound impact that Nobel Prize and well-known scholars may have in expanding the perspective of NTU faculty and students. Also, more important, in his mind, National Taiwan University is not only belonging to NTU alumni, but also generally recognized the most important university by Taiwanese. Therefore, he donated a total budget about 5.5 million euros in 10 years to support NTU on inviting Nobel laureates for delivering lectures and bridging the potential collaboration with NTU. His vision is to pave the way of Taiwan's academic institution to the world communities. It will also provide the informative research experience for our faculty and students, which could enhance the global academic influence. The Song Chair Professorship focuses on inviting the world-class scholars in areas such as semiconductor, data science, quantum technology, sustainable and green energies, precision medicines, sinology, legal studies, and more. This distinguished professor could collaborate with our faculty on teaching, research, and cultivating young scholars, as just mentioned by Professor Alain Aspect on that, therefore enhancing NTU global competitiveness. I would like to once again extending my heartfelt thanks to President Raymond Song for his generous support for this program. Also, I believe that we can benefit significantly on understanding quantum science and technology from the speech of Professor Alain Aspect. So thank you very much, and I believe we can benefit a lot from his speech, and thank you again for the support from President Raymond Song. Thank you.
Thank you, Dr. Chen. Today we are also so honored to have the person who made this exciting lecture possible, the founder of Light Technology, Mr. Raymond Song, joining us today to share his vision. Mr. Song, please come to the stage.
Yeah, good morning. I think I better say Chinese. 很多的算是人性我们校长还有 Dr. Aspect， 今天呢非常高兴的来参加这个聚会。
Mr. President, Professor Aspect, it's a great delight to be here, join you all together.
事实上，今天这个聚会的源头，是从陈校长呢。我跟陈校长呢是从来不认识，但是呢，陈校长呢，经过我一个朋友，跟我见面，见了2到3次，他一直希望，我对台大的学士有一些努力贡献。
Today's program and story began with me meeting President Chen. I didn't know him before, but when the two or three times I met with him, he always talked me into supporting and contributing to the NTU's academic development.
所以我深受感动，我就静下心来，在思考说，台大是台湾的最高的学府，到底台大在现有的阶段需要的是什么？那我经过不断的思考，我觉得说，就像陈校长告诉我的，台大是台湾人的最高学府，是台湾人的台大，那针对他这样的一个话语，我就更深入的去思考，台大如何更进一步的变成台湾最高的学府，是属于台湾人的台大。
I'm deeply moved by his will to improve the NTU's various endeavor. As he's always said, that NTU is the biggest and the best university in Taiwan, and I'm constantly contemplating what it really needs to excel further. And because for Taiwanese and Taiwan as an entity, then the better the university is going to be essential for the entire country.
所以我思考了以后，我觉得说，台湾事实上，它的资源很少，但是今天台湾的高科技，像现在最流行的，大家在谈的所谓的半导体，像 AI 等等的产业，都几乎是 引导着世界的这个步伐往前进。那这个背后主要的原因因为台湾的资源非常稀少，台湾能够有今天的这样的一个成果，背后最大的原因是台湾的教育真的做得非常成功因为有好的教育基础，所以造就了今天台湾在各行各业都让世界各国对台湾得到很高的肯定跟尊重。
After thinking about it, Taiwan as an island with very scarce resource, it succeeds in various technological fronts like semiconductor, artificial intelligence. We are leaders in many aspects of that, and the main reason for that success is education and having a good educational system. So our success owes a lot to that part of the society.
所以我想说，那台大要继续领导台湾的高等教育的龙头往前走，可能最重要的是就是说，邀请在世界各国非常有成就的教授，像诺贝尔得奖这一类最高成就的人，能够到台湾的台大来这边开讲座。那这个讲座的目的是希望帮台大开一门另外的一门大的窗子，让台大的学生他的眼界他的心思他的思维比现在更远大更宏观。
For NTU to continue to lead the previous mentioned successful endeavor, I hope to, through the program, invite eminent scholars in the world, such as Nobel laureates who are the highest successor in that area, that with their input and coming, NTU can open a big window for students to see more and open up their minds to new ideas and thinkings and for their improvement.
台大同时也可以跟世界的名校有更密切的来往，还有台大的学生也有更多的机会到世界各国的好的大学做学生的交换。
With that connection built, the NTU can connect with more prestigious universities across the world, and its students have opportunities to visit and exchange with those universities.
所以今天的机会，我们谈到，我们谈的好像是，我的讲座。事实上呢，今天呢最重要的指教是陈校长，因为所有的源头，都是因为陈校长的使命感，还有他的热心，才造成今天大家有这个机会，非常喜悦的同济一堂。所以，我在这边呢，也跟各位来宾讲，大家真的非常有福气，在这段时间里面呢，陈校长呢来担任呢台大的校长， 他的热心还有他的使命感，造成今天的机会。大家真的非常有福气。
Also, today's professorship is in my name, Raymond Song, but it's actually more about President Chen and his contribution and enthusiasm and his care for his educational mission, that NTU is so fortunate to have such a dedicated president willing to commit to the educational endeavor, and that concludes my remark. Thank you.
非常谢谢今天大家不拘一堂来参加这个讲座的开始。但是陈校长跟我讲，这个只是第一步，再过来呢有好多的诺贝尔奖的学者，他们呢将会到台湾来，甚至于呢到不同的大学里面去成立讲座，那这些事呢我听了以后，觉得非常的喜悦，也非常的感动，我只是幕后的一个扮演者，事实上呢，如果大家呢觉得这个是一个有意义的事，所以要谢谢的就是陈校长，他在这段时间里面非常用心，非常不断的努力造成的结果，所以我在这边呢，也要谢谢陈校长你的用心，然后谢谢大家，祝福大家身心愉快，谢谢。
Thank you for being here and participating in today's event. As President Chen mentioned to me, that this is only the first step of a series of Nobel laureates visit, and today marks the exciting first one. And it's such a great joy and delight to hear that all planned out, and President Chen has really devoted a lot to our development, and I'm so appreciative of everything. And thank you all, and have a great day. Thank you. Now for the main event, we'll have Professor Aspect back to the stage to deliver his inaugural lecture, From Einstein and Bell to Quantum Technologies, Entanglement in Action. Let's give another round of applause to welcome.
Okay, as I told you, it will be a serious scientific talk. I will try to explain you what was this fantastic debate between Albert Einstein and Niels Bohr, which first sounded to be only a question of philosophy, interpretation of quantum mechanics, but thanks to John Bell, became experiments, and these experiments eventually lead to new ideas about quantum technologies. So it's a fantastic example of how going from the most abstract, the most fundamental discussions, at the end you get technologies. So I think it's especially appropriate for the first lecture of your series, because you support the university because you want to support fundamental research, but also, of course, you are motivated by applications of fundamental research. This is exactly what it is about. So, how did these new quantum technologies emerge? It started in 1935 with a debate between Einstein and Bohr, but the major point being the discovery by Einstein and his colleagues that if you consider entangled particle at a distance, it's really very, very strange. Schrödinger immediately understood that it is definitely amazing, and he wrote a paper to see it's yet more amazing than you think. 29 years later, John Bell discovered that entanglement is not only amazing, but different from anything they thought about quantum mechanics up to that point. He did what I call the starting point of the second quantum revolution. Everything they knew up to that point was a first quantum revolution based on wave-particle duality. Here, it will be a second quantum revolution based on entanglement. It took another almost 20 years for Feynman say, okay, if it is so new and so extraordinary, there should be a way to do something with it. And it was the starting point of ideas of applying entanglement to do some technological stuff. And so entanglement, indeed, is at the root of many quantum technologies which are permitted by the experimental progress in observing and controlling individual quantum objects. And so are we living a new quantum revolution? Well, I will give you my answer at the end of the talk. So I will start with the Einstein-Podolsky-Rosen-Bohm-Gedanken experiment, thought experiment about strong correlation at a distance, Bell theorem, Bell experimental test experiments showing that we have to renounce local realism, which was the vision of Einstein, and showing just an example of the fact that quantum non-locality sounds crazy, but it gives some people, including me, it gives intuition leading to applications. And so I will try to ask the question, are we living a new quantum revolution? Okay. So this was the initial question of Einstein. Is it possible, or yet necessary, to explain the probabilistic character of quantum predictions by completing quantum mechanics at an underlying, more precise level of description? And this underlying level would introduce unknown quantities called hidden variables or supplementary parameters. Just to make things clear, Einstein had no problem with probabilities. He wrote a wonderful paper in 1905 about the Brownian motion, which was a masterpiece for using probabilities. But he thought that the fundamental theory should not be probabilistic. For instance, if I want to describe the distribution of the velocities of the molecules that I have in that room, I will use probability, so-called Boltzmann distribution, to say probability to have molecule with a velocity between 300 and 310 meters per second, probability is 3%, etc. So probability is convenient, but we have no doubt that each individual molecule has its own velocity. And in principle, we should be able to describe all in details. That was the idea of Einstein. Because it is a probabilistic theory, it should be a statistical theory of some underlying level. The discussion started in 1927 at the Solvay meeting, and each time Einstein came with a so-called Gedanken experiment, thought experiment, and saying, you see, Bohr, we have to introduce something more precise than quantum mechanics. Each time, Bohr came with a convincing rebuttal, okay? But all this was about a single particle and the so-called Heisenberg relation about a single particle. In 1935, so Einstein accepted the fact that Bohr has been successful in refuting his discussion. But in 1935, Einstein came again with his colleague Podolsky and Rosen. It was now a Gedanken experiment and a thought experiment about two particles. And there, the reply of Bohr was not that scientific. It was more about epistemology, about philosophy, about the conception of the world. And so Einstein was never convinced by the reply of Bohr. And there are some scientists who were never convinced, John Bell, and I belong to that category of people who think that the reply of Bohr is convincing only if you accept the philosophy of Bohr. But if you don't accept his philosophy, it's not a scientific demonstration. Let us start and go to science. I describe two entangled particles, and I take the example of two photons because the experiments have been done with photons, so it's better to start with the example. So I have a source emitting a pair of photons. A photon goes to the left, a photon goes to the right, and I will perform polarization measurements on each photon. Most of you know what is polarization. When light propagates, if you think of an electromagnetic field, the electric field vibrates in a plane. So it belongs to a two-dimensional space, the plane which is here. And if you measure it, you can describe it with two axes, x and y. And when you measure it with a polarizer, if it is polarized along x, the beam will go out in +1 channel here. If it is polarized along y, it will go out in the -1 channel. And if you have an ordinary beam, if it is polarized at an angle, a fraction will be up and a fraction will be down. But if rather than a wave, if you have a single photon, the single photon will not be split in two. It will either go up or go down. And the only thing you can calculate with quantum mechanics is the probability to find it up and the probability to find it down. And this is this experiment. In this experiment, we have two individual photons. They are in pairs, they are emitted simultaneously, but then what you do is you look where it goes, and you repeat the experiment, and at the end, you have measured the probability. Probability to go up if the polarizer is on orientation A, probability to go down in orientation A, etc., for the two polarizers. Now, most interesting, as you will see, are the joint probability. Probability to get +1 here and +1 here when polarizers are in orientation A and B, okay? And this is the result. Don't panic, Monsieur le Directeur du Bureau Français, he is not exactly a physicist. Don't panic, I will comment. So we have the result of the calculation of quantum mechanics when you have that state, which is a state that was discovered by Einstein and his colleague, an entangled state. What is special about that state is that you cannot attribute a property to the first photon and a property to the second photon. It's only a global description. I comment a little bit about that because it's a crucial point. These are the notations speaking of the state of the two photons. The state XX describes two photons polarized along X. And so if you measure, you will find the result +1, +1. The state YY describes a pair of photons polarized both along Y, okay. And if you do a measurement, you get -1. What Einstein and his colleagues discover is that XX is an acceptable state, and if YY is a good state, then the superposition of the two should be also an acceptable state. But then you cannot say it is one photon doing this and another photon doing that. It's impossible to factor that state into a component attributed to the first photon and a component attributed to the second one. It's only the global description which has a meaning. In a sense, it is as surprising as a Schrödinger cat, which is both dead and alive. Here, it's a pair of photons which is both this and that. And I cannot make hand waving to show what it is exactly. Okay. When you have such a state, you can do the calculation in quantum mechanics. It's quite easy. And the result of the calculation is written here as a function of the angle between the two polarizers. Don't look at that too carefully. The important thing is now what you have. If the two polarizers are oriented along the same direction, so the angle AB is 0, then look at the formula and you find that P plus plus equals P minus minus equals 1/2. And the crossed probability, plus minus, is 0. This means total correlation. Maybe you don't appreciate that it is total correlation, so I will elaborate on that. Because you say, well, 1/2 is not total. Yes. The single probabilities is 1/2. So when the photon arrives here, it has 50% chance to go in +1 channel. But then the joint probability is also 1/2, which means that the conditional probability to get +1 here, if I get +1 here, this conditional probability is 100%. In other words, the two photons arrive. Until the last moment, this is very important, until the last moment, they can give +1 or -1. It's random, but at the last moment, a decision is made. If it is +1 on this side, then it is +1 on this side. And if it is -1 on this side, it is -1 on this side. This is non-local correlation. We are scientists, so we need to measure things, and the correlation coefficient, you calculate it as predicted by quantum mechanics. I have the feeling that my arrow is lost. Do you see my arrow? No? It is lost? Okay. Let me see where. What? Here. It is here. Okay. We need to define a correlation coefficient, which is this formula. The important point is that we have a formula for it. It's the cosine of 2 times the angles, and you see that if the angle is 0, the correlation coefficient is 1, which means total correlation. Okay, so this is what is written here. Okay, now, I want to understand. And the question is, what does it mean to understand? Some people will tell you, you do the calculation, you have a result, and that's it. It is a school of thinking called shut up and calculate. Many physicists belong to that school. They say there is no need to go beyond the shut up and calculate, do the calculation, there is no need to go away. I don't belong to that category. I want to have images. And so I have a calculation, I try to develop an image from the calculations. I cannot develop an image by the simplest way of doing the calculation, which is written here. Some of my colleagues will understand what it means, but the important point is that this calculation is done in an abstract space, which is totally different from the space where we live. As a result, we don't know how to make an image in our space from that calculation. On the other hand, as written in this excellent book about quantum physics, quantum mechanics, more precisely about quantum optics, he writes, quantum phenomena do not occur in an abstract Hilbert space. They occur in a laboratory. So I insist, I want an image in my laboratory. I have a source here. I have a detector over there at 6 meters. I have another detector there. My 2 photons are emitted from the source. I want to understand what happens when the photon arrives here, when it arrives there. I want such an image. And then there is a possibility to have an image, and you will, I hope you will appreciate it. In order to obtain an image, I will suppose that this polarizer is a little closer to the source than the other one. And so, okay, I look at the time. I don't know how long, well, I thought I had a clock on my screen, but I don't have. Okay, so, okay. That's okay. So I do a measurement here first, and then I know I can get result +1 or -1 with the same probability. If I get +1, and if the polarizer is along X, it corresponds to the state X for the first photon. Now what do? I go to my reference textbook, okay, and I look at the postulates of quantum mechanics. And there is one postulate which says that just after a measurement, you should take the initial state and project it onto the eigenspace associated to the result of that measurement. Whatever the word, the result is that one. If you get +1, immediately the pair of photons is described now by XX. And this is very clear. The second photon will be also measured with +1 along X. But if the result at the first photon, for the first photon is -1, corresponding to polarization Y, then immediately after the measurement, then the second photon will be along Y also. This is what I learned by applying the postulates of quantum mechanics. And so, you see what we have. Okay, we can go on, and we have an image now in our space for understanding or for describing this correlation. But there is something that Einstein did not like at all. In that image, the measurement on the first particle seems to influence instantaneously at a distance the state of the second photon. This is non-locality. This is quantum non-locality. It was not acceptable by Einstein. But on the other hand, you can have a simple image based on our ordinary world. Let's suppose that you have two particles which are emitted, they propagate, and then you have strong correlation between the result. You are going to say it's very simple. They have a joint property determining the result. For instance, from the beginning, the two particles were XX. So you get +1, +1. Then next one is YY. Then you get -1, -1. So the idea is to have a joint property determining the result of the measurement. This idea is extremely natural and scientific. This is the idea that the biologist, medical doctor used before deciphering the genetic code. Okay, there was a time when you could not read the genetic code, but when there are twin brothers having the same property, color of eyes, color of hair, or same disease, okay? They concluded that this was due to common chromosomes, okay? And of course, now they can check that real twins have common chromosomes. So you see, this image is extremely appealing because it gives you a non-crazy description of what happens, not this strange non-locality. With this, you could have a good explanation. Bohr did not like that at all, because Bohr had the intuition that if you complete quantum, this amounts to completing quantum mechanics. You introduce the famous supplementary parameters, the finer description. Bohr did not agree because he had the intuition. We cannot say more than the intuition. He could not demonstrate it. He had the intuition that if you complete quantum mechanics, something will become wrong in the equation at some point. But he could not demonstrate it. This discussion lasted until the death of Bohr and Einstein. Bohr could never convince Einstein, and Einstein could never convince Bohr. It's clear by all their writing. But they went on, this was their major discussion all along the years, okay? And other physicists did not care. Why? First, because quantum mechanics was accumulating success, but I think that the most important reason why they did not care is because at that point the discussion sounded purely philosophical, epistemological. It was about interpretation. There was no debate about the way of doing the calculation. Einstein used the formalism, the mathematics of quantum mechanics, exactly as everybody else, as Bohr, as all the other physicists. So you are a young physicist working every day in your lab, you do the calculation, it works, you know that there is a discussion, but the discussion is about philosophy. You say, okay, when I am old, when I am retired, I will think about that, okay? But at the moment, no need to do it. So no attention from most of the physicists, except one, John Bell. John Bell said, let us take seriously, I have lost, okay, it's here. Let us take seriously the hypothesis that I have a joint property lambda to describe the measurement. What should I have? I should have a function depending on lambda and on the orientation of the first polarizer, which can take either value +1 or -1, and it tells me what will be the result of the measurement. Same thing on the other side. Extremely simple and reasonable. You cannot do simpler. And then, of course, the various pairs have different lambda, so you need to describe the probability distribution of the various lambda with a density of probability which is positive and which is normalized. And with this, you can calculate the correlation coefficient. With a simple model of that kind, you can find the result which is described here by the red curve. It's an extremely simple model, okay? And with this very simple model of that kind, well, you see, you can describe the full correlation for angle 0. You can describe the fact that the correlation is 0 at an angle of 45 degrees. You can find the full correlation as an angle of 90 degrees. The fact that it is -1 just means that when you have +1 here, you have -1 there. But because you have crossed the polarizers, -1 corresponds to the same direction. So you see, you have the very simple model giving the result of the red curve, which is very close to the prediction of quantum mechanics. And so you ask yourself the question, can I find a more elaborated model? Is there a better hidden variable model agreeing with quantum mechanical prediction, not only at 0, 45, and 90 degrees, but agreeing exactly on each point? And the answer is given by Bell theorem. This is Bell theorem. Bell's theorem is, the answer is no. There is no way to have a model, whatever sophisticated it may be, reproducing all the prediction of quantum mechanics. I like very much this photo of John Bell in front of a scheme of an experiment, and the scheme of that experiment is exactly my experiment. And it was not my photo, it was a photo released by the Nobel Committee. I was very proud that they selected this photo. So there is no local hidden variable theory in the spirit of Einstein local realism that can reproduce quantum mechanical prediction at all the orientations of the polarizer. Okay. Just give you a flash of how it works. If you assume that the correlation coefficient can be described with lambda, any kind of theory with lambda, rho of lambda, etc., not a specific one, any kind, following that scheme, okay? Then there is a quantity S that cannot be bigger than 2 and that cannot be less than -2. And this quantity S is a combination of 4 correlation measurements obtained by considering 2 orientations, A and A prime on the first side, and B and B prime on the other side. And so you make measurement AB, AB prime, A prime, B prime, A prime, B. You have 4 numbers, you measure them, and you combine them with 3 plus sign and 1 minus sign. Why? Well, I don't know. Bell found it. Well, this is what he had to do, and he found it. Maybe he tried many things until he found that, but at the end, this is what you have to do. And then you take these 4 coefficients, and if you can describe the correlation with a joint property, then S shouldn't be bigger than 2. On the other hand, remember the prediction of quantum mechanics, E equals cosine of 2 times the angle. If you consider this orientation, 22.5 degrees, 22.5 degrees, and 22.5 degrees, 2 times 22.5 is 45, and cosine of 45 is 1 over root 2. So what you get is 1 over root 2, 1 over root 2, 1 over root 2. But if now you look at A, B prime, and you double the angle, most of you will realize that then you have minus 1 over root 2, and here you have a minus sign, so you have another 1 over root 2. And the result is S, predicted by quantum mechanics, bigger than 2, equals 2.8. So there is no way with the supplementary parameter theory to reproduce this prediction of quantum mechanics. That Bell's theorem. Okay. So the conflict is here. The possibility to complete quantum mechanics according to Einstein ideas is no longer a matter of taste, no longer a matter of interpretation. It has turned into an experimental question. Okay, this is a demonstration of Bell's inequality. If you ask it, I will show at the end. Okay. Now, the important thing for me, to demonstrate Bell's inequality, there is an hypothesis which is necessary, which is called Bell's locality condition. It is a fact that the result of the measurement here is not allowed to depend on the orientation of the other polarizer, which is far away. And simultaneously, or similarly, the result of the measurement here should not depend on the orientation which is here. This is written here. And also, when the 2 photons are emitted, the supplementary parameter lambda distribution should not depend on the orientation of the polarizer that will do the measurement later. This hypothesis is reasonable, but Bell stressed in his first paper, and it is what I read, and it is what motivated me, he stressed that if you could do an experiment in which you change the orientation of each polarizer while the photons are flying towards the polarizer, then there is no time for any information to go from one end of the experiment to the other one, and then the locality condition would no longer be an hypothesis. It would become a consequence of Einstein's relativistic causality. Okay. So in an experiment with variable polarizers, you would have a full conflict between quantum mechanics and Einstein's vision of the world that we call local realism. I will speak about that later. Okay. So with Bell's theorem, we can do experiments. There was a first series of experiments by pioneers, John Clauser in Berkeley. He got the Nobel Prize 2022. Then there were a few discussions, but all these experiments were wonderful, but they were still quite far from the scheme that I've presented. And this is why I embarked in 74, 75 into a series of experiments, and the goal was to develop experiments closer and closer to the scheme discussed by theorists, okay? And so the first thing was to produce a source of entangled photon much more efficient than the previous ones, okay? And so I could do schemes closer and closer to the ideal Gedanken experiment, including demonstrating quantum non-locality. Then, you see, my last experiment appeared in 82. Then it took almost 2 decades for people to develop a 3rd generation experiment based on a source of entangled photon, yet better than my source, okay? It's always a question of good signal, you know that. And so with their source, they could do experiments yet closer to the ideal scheme, and with that, they could do what they call loophole-free test of Bell's inequality, which was published in 2015. All this is the opportunity for me to emphasize the fact that between fundamental research and developed technology and application, there are decades. We have plenty of examples of that. Okay, so this is just a view of the experiment I developed in Institut d'Optique. The idea was to produce a 2 photon in what is called an atomic cascade. That is to put the atom here and you have a cascade. First photon, second photon. And if you choose well the intermediate levels, then you have the addition of the 2 paths. That's a fundamental quantum mechanical law. And at the end, you get exactly the state you want to have. It was quite complicated. I had 3 lasers, exciting atom flying in a vacuum chamber, the so-called atomic beam. But I had a beautiful signal. And with this beautiful signal, I could reach an accuracy of 1% in less than 2 minutes, which is fantastic. Clauser took hours to have this, okay? And so when you can get it in 2 minutes, life is comfortable. Okay, and so it allowed me to do various experiments. For instance, this one, which looks like the ideal scheme with polarizer and passing the +1 polarization and reflecting the -1. Believe it or not, but it was the first time, it was in 81, it was the first time that an experiment of that kind was done. So it was my first new scheme. Violation of Bell's inequality was absolutely fantastic. Violation by 40 standard deviation, okay? This, the result of the experiment, in line with the prediction of quantum mechanics and violating the Bell's inequality by more than 40 standard deviation. 40 standard deviation is impressive. You know, in CERN in Geneva, when they have a signal which is above the background by 3 standard deviation, they don't publish, they leak the information that maybe they have observed something. When it is 5 standard deviation, you publish. Here it was 40 standard deviations, so no discussion. Last experiment, the one that I wanted to do from the beginning, and the one which granted me the Nobel Prize, direct demonstration of non-locality. The idea is that you want to change the orientation of the polarizer while the photons are propagating. It takes 20 nanoseconds. So you have to change it in much less than 20 nanoseconds. So if you look at the kind of polarizers that you have, it's a big system like that, several, like 20 or 30 kilograms. Even when I was young, I could not switch 30 kilograms in less than 10 nanoseconds, okay? So the idea, sure. The idea was the following. If I could build a switch sending light either towards the first polarizer in orientation A or towards another polarizer in orientation A prime, if my switch is fast enough, then it's equivalent to a single polarizer change from A to A prime, back to A prime, etc. It was not easy, but I could build such a switch. By the way, no company could deliver it. I had ordered it, they could not deliver. At the end, they say, okay, we return you the money we cannot build. So, you know, a researcher always has a solution, so I could build it. Well, I will tell you if you ask me the question, the solution was simple. Okay, anyway, it was a difficult experiment, and in this experiment, for the first time, we had a convincing result. Bell's inequality were violated by 6 standard deviations, and for the first time, we had each measurement separated by the other one by what is called in relativistic theory space-lag separation. That is, no signal can connect them, or it should go faster than light if you want to have a signal connecting them. Okay. There was a third generation of experiment. As I told you, there was a next progress, an important progress in sources of entangled photon. To make a long story short, but it is extremely important for application. In my source, photons were emitted in all directions in space. So I needed to have lenses and collected the photon. With a new kind of source that it took more than 10 years for them to develop this source, the production of the entangled photon was based on parametric down-conversion, which is a nonlinear effect. And the main result, or the main property of this parametric joint conversion is you take an ultraviolet photon, you split in two, and the two photons are going to be entangled, but the important point is that they are emitted in a well-defined direction. So well-defined that you can inject them into optical fibers. And as soon as you have them in optical fiber, you can go to 200 meters, several kilometers, etc., and check that you still have entanglement. And you realize, of course, that for quantum technology, it is essential to have sources of entangled photon that you can feed into optical fibers. You have now cases where people inject entangled photon in commercial networks, and entanglement is still there. So it's the route towards applications. Okay. So there have been many discussions about loopholes, closing loopholes, etc. And for those of you who are interested by this discussion, I can tell you that I wrote in detail my comments about this experiment, which eventually came out in 2015, so-called loophole-free Bell test experiment. And this is expressed in this viewpoint published in a journal online, which is the News and Views of the American Physical Society online. It's free. So you look for it, and I discuss in detail how to consider these experiments. I am very positive on it. Okay. So the conclusion is that Einstein's local realism is untenable. What does it mean? Well, we just have to ask Einstein. And at this point, you are going to be surprised. Einstein thought that he was not right. No. Einstein was smarter than that. Einstein made reasoning ad absurdum. He said, if I was not right, this is what you would have to accept. It's so incredible that obviously I am right. That was the reasoning of Einstein. So let us look at what he said we would have to swallow if he was not right, because we know he was not right. So Einstein had considered, okay, in order to reject it by reductio ad absurdum, the consequence of the failure of his reasoning. And he said, if quantum mechanics could not be completed in the spirit I am suggesting, you would have to accept the following thing. Either drop the need of the independence of the physical realities present in different parts of space, I will comment, okay? Or accept that the measurement on the first system changes instantaneously the real situation of the other one, which is distant. These two wordings are, in a sense, more or less equivalent, but it is interesting to separate them. This is what I do, because they lead to two different classes of applications of quantum technology. The first one, quantum holism, the fact that the property of a pair is different from the sum of the property of the first one and the second one. You cannot describe the pair as a system here with well-defined properties and a system here with well-defined property. The only thing you can do is to describe globally. This is at the root of quantum computing, because you have more information in an entangled system than in the sum of the components, and that amount of information increases exponentially with the number of entangled objects, and it suffices in principle of 100 qubits to store more information that you can do nowadays in all the computers that we have. And so the power of expected quantum, of dreamed quantum computer is based on that property of quantum holism. So the other property, the other way of speaking, quantum non-locality, gives rise to the applications which are quantum communication, quantum cryptography, quantum teleportation. This is based on the intuitive idea of quantum non-locality. I will show you an example. Okay, so let me just give you an example of how having images involving quantum non-locality allow you to understand immediately a method of quantum communication, which is quantum cryptography. So let us see what it is about. Cryptography is about two friends, Alice and Bob. They want to communicate, and there is a spy called Eve, an eavesdropper, you know, the guy who is listening. And you have the spy who is trying to intercept and decipher the message. And there is a mathematical theorem proved by Robert Shannon. He was a founder of the theory of information long ago at the time of World War II. Okay. Robert Shannon has demonstrated that you have an absolutely safe method for Alice and Bob to exchange messages without Eve being able to decipher the message. It is to use an encoding key, which is a random series of 1 and 0. And if Bob has the same key for decoding, then the security is total under one condition. The message should not be longer than the length of the key. Because if the message is longer than the length of the key, you will have to use the key several times. And there will be some kind of periodicity. And the people who do cryptography are extremely smart mathematicians. And they will be able to find that there is a periodicity, and at the end, they will be able to decipher. Okay? And so the problem boils down to the possibility to distribute to Alice and Bob the same random series of 1 and 0 at a distance. Because, of course, if they are close to each other, there is no point. They can directly talk to each other, okay? So they are far from each other, and you want to send them to identical copies of random series of 1 and 0 without the spy being able to have a third copy of that. Clear? Okay. Entangled photon will do the job. Because remember, now this is a modern source of entangled photon. Remember, if Alice and Bob have the same direction for their polarizers, it's random. It's either +1 or -1. But it is the same number on both sides. Either it's +1 or -1. Well, you can decide that -1 is 0 to have the language of a cryptograph people, and that's it. So what do Alice and Bob do? In advance, they decide to have a series of orientations. When it is finished, Bob sends message to Alice on clear radio. Everybody can spy. He say, oh, on the first case, this was my orientation. On the second case, this was my orientation. And then Alice say, okay, we take third case, fifth case, seventh case, etc., because it was the case when orientation were the same. Okay. Good. So now they have the two identical keys. What about the spy? Couldn't the spy try to intercept the value of the key? And the answer is no, because of non-locality. Remember, demonstrating non-locality is demonstrated that until the last moment, the decision is not yet made. Until the last moment, you don't know if it is going to be +1 or -1. So here there is nothing to spy. So the guy cannot get the third copy of the key. Well, I could refine the reasoning and tell you that in case he is so smart that he makes a measurement, he will leave a footprint and there will be no violation of Bell's inequality, and Alice and Bob can make a test to know that there is a guy on the line. But the important point is to realize that because of non-locality, the value of the key is not yet here. It will be done at the last moment. So this is an example of what I present as an intuitive image allowing me almost immediately to know this should be a good method. Of course, after you need to do full calculation, etc., as usual. But this is technical. The important thing is the initial intuitive idea. Okay. You may know that there is an experiment which has been done by our colleague Jian Weipan with a satellite called Messius. Okay? He has demonstrated at more than 1,000 kilometers that you can still exchange the series of the two keys. Okay? This is amazing. Okay, I will skip quantum teleportation. The only thing I can tell is just for people who understand what is. Well, no, let me talk. After all, it's only, according to my clock, it's only 50 minutes, and they told me I have 1 hour. So let me tell you a few things. What is quantum teleportation? It's not Star Trek. It's not me taking you and sending you in another galaxy. Okay, no, it's not that. But quantum teleportation is as surprising or as interesting. It consists of taking a quantum information and sending it without any loss to another place. Why is it important? Because quantum information is what is called the quantum state of the system. And the quantum state of the system, there is no way to know it in totality. If you do a measurement, you have only a part of the quantum system. So it's not a good idea to make a measurement in order to know the result. If you want to use that, it's better to transport it directly. A little like in a, optical fiber. At the beginning, they were sending a pulse, then the pulse was converted into an electric pulse, and then you reconvert from electric to light, etc. It was not efficient. And then they discovered the amplifier in line, the erbium doped fiber, in order to be able to keep the information in optical form. Okay. It's the same idea here. The idea is keep the information in the quantum form. If you have a first quantum computer, you look at the output of the first quantum computer, and then you want to inject it into a second quantum computer, okay? Keep it in the quantum form. There is a way for doing that. It's called quantum teleportation. And I don't want to go into details, but just by thinking of quantum non-locality, the fact that I do a measurement here on the first photon, which I have a pair of entangled photons, and doing this measurement here immediately does something on the other photon which is far away. But I need also to make an operation depending on the results that I have here. It takes some time because it will go through a classical channel to arrive here. So the important point is that I must put the second photon in a quantum memory, waiting for the result of the classical measurement to arrive. So quantum teleportation absolutely demands a quantum memory. It's something that people do not emphasize, but it's a fact. So if we want to use quantum teleportation, we need to have good quantum memories. And I often tell young people who say, what do you think would be very interesting to do? I think quantum memory is one of the things. We don't have very good quantum memories. We have just simple examples. And developing good quantum memory is a goal which is, in my opinion, is not a 50 years goal. It's a few years goal. And having a good quantum memory will be useful for so many things that this would be a good goal. Okay. To finish, do we have a new quantum revolution? And let me first say, what was the first quantum revolution? It was first a revolutionary concept, wave-particle duality. And it gave a scientific revolution. With this concept, physicists could understand the structure of matter. Most of you may know that by the end of the 19th century, people did not understand why matter was stable. because they knew that matter was made of positive and negative charges. And positive and negative charges attract each other. So if you have a classical way of thinking, matter should collapse because positive and negative charge attract each other, period. Okay. And in order to understand why the electron doesn't fall on the nucleus, just like a satellite eventually falls on Earth, to understand it, you have to think that the electron is not only a particle, but it's also a wave. And a wave, you cannot squeeze it to a very small dimension. It has to remain with a certain size. This is what prevents the electron of falling on the nucleus. So with this notion of wave-particle duality and Schrödinger equation, etc., developing this idea, the physicists could understand the mechanical, the electrical, the optical properties of matter. So this is what I call the scientific revolution. They could even understand some exotic property like superfluidity, superconductivity, Bose-Einstein condensate, and so on, you name it. There were a revolutionary application. I like to emphasize that the new devices named laser, transistor, integrated circuits were invented by the best physicists of the time, using quantum mechanics to describe how electrons propagate in matter. It's not the guy just trying in a garage, you know. No, it was the best scientist knowing perfectly well the theory of quantum physics. So it was not only a scientific revolution, but it was also a technological revolution. And you all know that this gave rise to our society of information and communication, which certainly changed our society as much as the heat engine changed the society in the 19th century. So you see, the first quantum revolution was not only conceptual and scientific, it was also technological. Now, what about the second quantum revolution? First, I must say that the second quantum revolution is not only using entanglement. I will not again say that it is important. Now you have understood, or you were sleeping, okay? So entanglement is important, but it's also about controlling, manipulating, and observing single quantum objects. Until 1970, nobody had ever observed and manipulated a single quantum object. And there was a general wisdom that, okay, in general, we have a large ensemble of quantum objects, and so there is no surprise in the fact that the theory to describe it is probabilistic. If it is only about large ensemble, it's good enough to have probabilistic predictions, okay? But by 1970, Hans Dehmelt in the United States was the first to be able to trap a single electron. He could trap a single electron in a trap like that, okay? Keep it for weeks, observing it, manipulating it. And then Don Eigler in IBM was able to manipulate single atoms at the surface of a crystal with an AFM atomic force microscope, etc. We were able to produce pair of photons. Then there was production of single photons, and Jean-François Sarok, who is here, was one of the pioneers in source for single photons, okay? And plenty of interesting things. And other way, this is, for instance, it's single infrared photons of my colleague Serge Haroche in Paris, okay? He received the Nobel Prize in 2012, okay? And plenty of things, and including now there is a big effort in trying to develop artificial individual quantum objects, qubits, by using superconducting circuits, okay? And I know that you have efforts like that in this country. And if it works, then you can use all the technology of the nanotechnology, etc., to develop it. Okay. So remember, second quantum revolution is entanglement plus single quantum objects. Okay. Is it really a new technological quantum revolution? Well, there are several fields. I already mentioned quantum communication. I alluded to quantum computing. Nowadays, we have only imperfect quantum computers. As you heard, I am a co-founder of one of the companies called Pascal, but there are many other companies trying to build a perfect computer, and for the time being, having only imperfect quantum computer, but you can do interesting things with imperfect quantum computer. So it's a good situation for that, okay? Quantum metrology, an example, I like it because here again there was a startup company founded by my former students. It's a gravimeter based on interference of ultra-cold photons. The sensitivity is better than any other apparatus, and it's so reliable that you can put it on the volcano, and they are trying to see if there is a correlation between fluctuation of gravitation and new eruption of the volcano. If it works, it's a major thing for humanity. And you have envy centers. Once again, Jean-François Sarroc, who is a regular collaborator with NTU, shows that you can use these envy centers for wonderful detectors. So these are the three branches. I'm deeply convinced that there will be applications. And the question is, will it be only niche application, or will it have a big market? I think that nobody knows. So at the point, there are a lot of discussion about quantum advantage. Quantum advantage is the idea that you could do with a quantum device what it is impossible to do with a classical device. And more specifically, when people speak of quantum advantage, they want to compare the quantum computers with classical computers. And most of the time, they focus on the possibility to do bigger and bigger calculations. This is what I call computing power, computing efficiency, okay? But there is another face of the coin. It's the fact that we have good reason to think that a quantum computer could do the same calculation as a big mainframe quantum computer, but do it with much less energy. And when I talk to young people who say, oh, you know, the urgent point is not to have a bigger quantum computer, is to save energy. I say, look, quantum computer can be a solution to save energy. So this is an open question, but it is, I think, an important discussion. So nobody can answer with certainty, will we have a big market, will it change society, will it change the ranking of nations according to the fact that they have this technology or not. But there are many of states, here I just take the example of France and Europe, but of course each country has its own program. Big companies which have a lot of money, and I visited a couple of days ago Foxconn, and Foxconn has also an operation for quantum information, okay? Plenty of startups, I cite only some of them, not all, and all that is fascinating perspective. I don't know the answer. Will it, yes or no, change the society? I don't know. I'm deeply convinced that we at least will have niche application. And with that, I must mention and give some thanks to the engineers in optics and mechanics which helped me, and electronics which helped me, the workshop of my institution, Institut d'Optique, and two young students, they were master students who came to help me in the last collection of data and participated to the data. And these people have become stars in the world. One is Philippe Grangier, the other one is Jean Dalibard. They are stars. And I was lucky to have them with me at the last experiments, but in a sense they were lucky also because I invited them to accompany me in Stockholm and take this beautiful dress for receiving the medal from the king. Thank you very much.
Thank you, Professor Aspect, for your profound and insightful speech. Please remain on the stage for the Q&A session as Mr. Professor Guan Xisen joins us as the moderator. Professor Guan.
Thank you for your presentation, and you're very experiment proved that the violation of the Bell's inequality.
Speak closer to the microphone.
Your experiment proved that the violation of the Bell's inequality and showing that quantum mechanics might be correct. And if that our board is behave the way that the quantum mechanics describe, then how can the measurement process exist? Because if all the things is this can be described by the probability, and why we can use a measurement to change this probability to become a classical deterministic result.
Okay. Probably if you ask this question, it's because you know that we don't have any answer. We don't have an answer to the question until the last moment. It may be +1 or -1. And what happens here that makes that we have +1 or -1? We don't know. There are several suggestions, but no one really convincing. And so, what can I tell you? I can tell you that it is still an open question, and just like the discussion between Bohr and Einstein, and then the discovery by Bell eventually led to another understanding or an improved understanding of quantum mechanics, which leads to quantum technologies, to applications. Maybe thinking harder about this kind of problem, somebody will have an excellent idea, which eventually will lead to some other kinds of application. Because again, you should not say, okay, quantum mechanics works, there is no point in thinking about that. Yes, by thinking about crazy, amazing conclusion of quantum mechanics, you can have ideas for new application. It is exactly what happened with entanglement and with the development of quantum computers. So maybe by thinking about this equation, there may be some crazy idea eventually leading to application. But there is one point I can tell you. One of the big mysteries of quantum physics is the fact that you don't see quantum mechanical feature at a macroscopic scale. I mean, the Schrödinger cat, there is nothing like a Schrödinger cat, because it's too big. Why is it that we don't observe wave-particle duality at a big scale? We don't know. It may be technological. It may be fundamental. For instance, Roger Penrose, with a smart theorist, sometimes proposes that when you quantize gravitation, then there are quantum fluctuation of gravitation, which can make decoherence on our system, which will allow us to understand the fact that when a system is big enough, the fluctuation of quantum gravitation are enough to provoke a decoherence, and so the Schrödinger cat is either alive or dead. I don't know, but this is a kind of question which is interesting. Nobody has a good answer. People have some partial answer, but nobody has a convincing good answer to your question.
Thank you.
I want to ask that, what do you think are the most prioritized beside of quantum memories in order to have efficient advancement in quantum technologies? And also I want to ask another question is that, do you think it's possible if we do research into quantum computing and quantum information, and during that research we can reveal more fundamental understanding of our universe?
Oh yes, to the second question, there is no doubt. When you work on quantum technologies, you have to be aware of the most profound discussion. So certainly you have that in the back of your mind. But on the other hand, when you have a concrete subject, you want to develop a quantum memory, you don't think every other hour to the foundation of quantum physics. You do your job. You know what John Bell said? John Bell said, during the week, I am a quantum engineer. he was not an engineer, he was a theorist. By a quantum engineer, he meant I use the quantum formalism of quantum mechanics as nobody does it. So during the week, I am a quantum engineer, I do my job. And on weekends, I look for principles. So this would be the recommendation. Take a subject with a clear goal, do your best for that clear goal, and from time to time, sit down and say, do I learn something about the foundation of quantum mechanics? Now, about your first question, if I understand well, you ask me, what is most important at the moment? Well, one point I want to, there are several research on hardware. As I said, different kind of qubits, different way of entangling them, etc. But there is also something which is very important, is quantum software. We need applied mathematicians. It's as important to have applied mathematicians to develop quantum information theory, because if tomorrow morning we give people an ideal quantum computer, a perfect quantum computer, well, we don't know exactly how to use it. We have some use cases, but it's not universal, in the sense that if you have a problem, it's not clear how to translate that problem into a program for a quantum computer. So we need also a lot of effort on that kind. And so, we need progress in quantum or research in quantum hardware, but we also need a lot of effort in quantum software. And the best thing, which is done in several companies, for instance Pascal, but many other companies, is to, I saw Foxconn the other day, the best thing is to have both people in the same place talking to each other. It's an extremely difficult research. You have to be ambitious to work on that.
Yeah, okay. Thank you very much for this wonderful talk. And I think you gave us a lot of inspirations here. Because if we go back to 1935, I think Einstein and Bohr would never imagine that the 20th century will have the first quantum revolution and give us all the semiconductors and all the current world. Okay? And now, this century, we're facing the second quantum revolution. Okay? And a lot of difficult work that has to be done, because for instance, in your 1982 experiment, and that was extremely difficult because the very fundamental physics with those transitions, and you were able to generate overcome all the difficulties that would prove this experimental results. Okay? Then after that, it took 40 years to get a Nobel Prize. So everything is kind of long-term when you do fundamental research, and it's extremely difficult. It needs a lot of support, but the outcome is kind of unpredictable. But once it's really accomplished, when the influence is really big. Okay, so I think maybe after this lecture, maybe the message you could give us is that we have to value very fundamental research, because those are extremely difficult work. And then with the support, and so we could imagine that maybe 20 years from now or 40 years from now, and we could have another new world with all the revolutionary devices or the way of life. Okay, so could you comment on that?
So you want, I comment about that. Of course, I 100% agree with what you say, but I will add something. I always did fundamental research because it's the only thing where I feel comfortable. I'm not gifted for finding applications. But with all my students, I always told them, we are doing basic research, but if you have a good idea for an application, you should go. Don't feel ashamed or embarrassed to go to applications. Doing application is as valuable as doing basic research. As a result, many of the startup companies and quantum technologies that you have seen on my list here, many of them have been founded by some of my former students because they knew, I encouraged them, you know, I was their mentor, and I say, with me you can only do basic research, but if you have a good idea, go. And this is why I am a co-founder of the Société Pascal, because when they wanted to found Pascal, they came and say, hey, you told us that it is good to do application, what do you think of that one? And I looked and I said, very good idea, and they say, come with us as a founder. You know, and so valuing fundamental research is extremely important, but the people who do fundamental research must tell the student that doing application is important. And maybe the idea will come from one of their students. This is my comment.
Considering of the time, is there any, that's just one last question. Is there any one last question on the floor? Over there. Okay.
Hello, Professor Aspect. You have mentioned that in the end of your lecture that many large technology companies have invested a lot of money in quantum computing research, and also they have a lot of progress. Do you think that universities have any advantages when competing with those technology giants? Thank you.
I don't think that it is a competition between university and these people. I think it's a joint effort. You know, building error-corrected, perfect quantum computer is such a big effort that it will not be successful if there is no collaboration between the best researchers in university and the best engineers and researchers in these private companies. And I can tell you, it is really what happens. In France, for instance, we have a company which is not in very good shape, but anyway, they have a good department on quantum computing, and these people collaborate all the time with the people at university. And if you take a company like Pascal, when they founded, they started in our institute, then when they grow up, they go to a place which is a few kilometers from us, but there is all the time discussion. So it's not a matter of competition. It's a matter of collaboration. Each one has its advantage. University people can think in the long term. They don't have to produce something next week or next month, and so they can think in the long term. On the other hand, in the company, the engineers have to solve technological problems. It takes time. Solving technological problems takes a lot of time, okay? But they can concentrate on having an apparatus which at the end is a push-button apparatus that the mathematician can use. And all this is a complete, we call it an ecosystem, when you have all these components. I don't know if there will be ever a perfect quantum computer, but if there is one, I am pretty sure that it will come only from this kind of collaboration.
Thank you. Let's conclude the scientific Q&A session here. Let's thank the Professor Aspect again.
Thank you.